welcome everybody to my presentation on early code coverage analysis using RISC-V virtual platforms. My name is Lukas and I'm from a company that is called MachineWare. And yes, let's get started. So I want to start with a little bit of a motivation. So sometimes I Google and I look what's happening in the industry. And I think we all know that we see a lot of headlines in the news about software issues, and especially in automotive it seems to be pretty pervasive. I think if you go today into a car dealership and buy a car, the first thing that you check is if your phone connects to the car, and if that doesn't work, probably you will not buy it, right? So software is very important, and having good error-free software is very important. The issue is that the complexity of software has been increasing exponentially over time, especially in the automotive industry. In the 1980s, there was only very limited amount of software in cars, maybe a little bit for the motor control. But over time, the amount of software in cars has just been going up and up. And today, in the era of the software-defined vehicle, a modern car has more than 100 million lines of code that run on it. And also, as I mentioned before, software is becoming the unique selling point of the car. So having good software is important to make people buy your cars. Also, bad software is quite dangerous and also very expensive. So when your software is not good, you have to recall, it hurts your brand image. And so managing software complexity is definitely one of the big challenges that we see today. The big issue is that the testing of software is inherently hard to scale, especially if you look at complex systems like automotive, because, well, the hardware resources that you have are quite limited, the test rigs are very expensive, and yeah, this is an issue that we have to overcome, but fortunately, there is a solution to that, and that's called virtual platforms. Basically, a virtual platform is full system simulation. It means it is basically a digital twin of your electronic system, and it has become an indispensable tool in modern software development, especially due to the ever-rising complexity of software and hardware. There are many benefits to using simulators or virtual platforms for software development and verification. Of course, and that's I think quite obvious, they can be available a lot earlier because you don't have to wait for your hardware to be completed before you can use a simulator. So they enable something that we call the shift-left methodology, basically allowing you to start software development and software testing a lot earlier and then coming with already more mature software to the hardware once it is available. Also, they are, of course, a piece of software, so they are very flexible and they allow very deep introspection in the simulator. You can press pause anytime and look exactly what the system is doing. Also, they allow for non-intrusive debug, so you can attach debuggers to it and you can check what the system is doing. And last but not least, and that is the issue that I mentioned before, they are extremely scalable. So if you have a simulator of your system, you can easily copy it 1,000 times, 10,000 times, and run it in the cloud to parallelize all your testing. So virtual platforms are a very useful tool, and they can be used for something that is called code coverage analysis. So I want to explain a little bit what code coverage analysis is. Basically, code coverage analysis gives you measurement of how complete your software testing is. So you have your software, you execute your test cases, and then you measure how many lines of your software code were executed when you were running your tests. And of course, you want to achieve 100% coverage so that you know that all lines of your software have been covered by your tests. That's the most simple definition. There's more advanced forms of code coverage, but let's stick with this definition for now. This code coverage analysis is a very well-established methodology, and it is also often a requirement for compliance with standards like ISO 26262. And basically what you do in code coverage, I mean, it's depicted here on the right-hand side. You have your software test and you have your target software under test. And you run your tests against your target software and generate trace files from that check or that contain how your software was executed. Then you pass these trace files into a coverage tool, and you generate something that is called a code coverage report, and it looks somewhat like this. Now you can do this on real hardware, but of course you can do it also on simulators, on virtual platforms, and it has a bunch of advantages to do it on the simulators. Of course you can do it earlier, because you can do it without the hardware, but also you don't have to instrument your software. You can do the code coverage analysis non-intrusively, and yeah, that is something that you usually don't do when you run the code coverage analysis natively. Also, I mentioned before, it's parallelizable and scalable. And that's also something that we are going to see in the demo later. You can take input to the virtual hardware into account when you run your tests. So for example, when you have a test case that involves CAN frames or Ethernet frames coming to your virtual platform and therefore to your software, you can measure the code coverage in these cases as well. And I will show it in the demo a little bit more clearly what I mean with that. So how do we do code coverage analysis using MachineWare tools? Basically, we use a virtual platform, a simulator, that's depicted there on the left. And we have two things that we pass to the simulator. On the one hand, of course, it's the target software that we want to analyze. And on the other hand, it's a script, a test that instruments the simulator and defines the test case. Then we execute this, so we execute the simulator with our software and our test case, and from this we get a trace file. And this trace file we feed to a tool that is called VPCov, and this tool can then generate the coverage report from that trace file. And in the end you get a nice looking coverage report. I brought a little demo to show how this works, and this is what we are going to see in the demo. So as a software in the demo, we have the Zephyr real-time operating system and a server application that is running on top of this Zephyr real-time operating system. This server application is a program that has a TCP/IP interface. So it uses the network connection to receive data from the outside, from a client. And we take this software and we run it on the virtual platform that we see here on the right-hand side. So this is a simplified diagram, but basically we have a RISC-V system that has a CPU and a bunch of interfaces. And among these interfaces is also a network interface. And this is the network interface that the server application is using. So via this network interface, you would receive the data that is processed by the application. In our simulator, we can do a nice thing. We can connect this network interface to the simulator host network and then connect the client application there. So we can run our software on our simulator and connect to this server application from the outside, which means we can feed it input. And from this, we can get the trace file that I mentioned before and then generate the code coverage report. So let's see how this looks in action. At the top here, and we'll start in a second, at the top we have the simulator, so in this case our Sim5 simulator, which is this RISC-V platform that I showed, and we pass it a configuration file for Zephyr. And in the bottom we have our client application that talks to the server application that is running on top of the simulator. So let's see how it looks like. So first we start the simulation, and you can see we booted the Zephyr. Let me just pause right here for a second. So we started the simulation at the top, and you can see we booted the Zephyr real-time operating system, and we launched the server application that is now waiting to receive data from the client. Then we started the client and connect to the server application, and we can send commands to the server application that is running on the simulator. And now we send some commands and interact with this server. And all while this is happening, and here we use only the G command, all while this is happening, we generate this trace file. Then we launch our tool and generate the code coverage report, and then we can get the code coverage for the entire platform. So this is the source code of the server application, and you can see here at the bottom, since we sent the G command to the server application, this part is covered. So our test case executed this code. But you can see there's also a lot of other commands in our server application that are not covered. These uncovered commands, we didn't execute them, so the code coverage is not there for these parts of the server application code. But we can run the test again, So let's start again the simulator, run the server application on Zephyr, and now we'll send different commands like the G command and the M command and also now the H command. And again, generate the trace file, and from this now generate the code coverage report. And again, we can check the report and we can see that the coverage of our server application is now much better, and we have also covered all the other statements that have not been covered before. So this kind of demonstrates how you can get the code coverage information on the virtual platform and then also use test inputs that come via usually physical interfaces like Ethernet or CAN or other interfaces, and take these also into account when doing the code coverage. And that's something that would be a lot more complicated to do on physical hardware. On the simulator we can just do it on any computer, and we don't need the board and nothing to get this information. So let me summarize what I showed today in this presentation. So virtual platforms are an ideal vehicle for coverage analysis. They don't require any special instrumentation in your software, so you don't have to change the software that you're running in your coverage test to get the coverage information. They are also extremely scalable. So I showed you in the demo that was more like an interactive case, but of course you could also just automate this testing and then run it on a server farm in parallel, and you could integrate it into continuous integration and do all of this automatically. You can do it pre-silicon, so you can do it entirely without the hardware, and you can start this code coverage analysis even before you have hardware available. And you can take into account inputs from your virtual hardware like I showed in the Ethernet case. As I said, you can integrate the entire simulation solution into a continuous integration system like Jenkins or GitLab CI, and then get these kind of tests running on every single commit that you make on your software. And also our tool generates a standard output. So the generation gives you in the end a standard report that you also get when you use other coverage tools. So that would be it from my side. Thank you very much for coming to my presentation, and if you want to learn more about this, feel free to visit us at our booth right over there. Thank you.